The topic we're going to be looking at is lesson number 4, conservation of momentum in 2D. The thing that I want to emphasize here is that this isn't really something totally new. It's still just conservation of momentum. It's still the idea that whatever momentum we have at the start, we have to have at the end for totals. The difference here is that now we're breaking things up into components because it's a 2D collision. We're going to be talking about something that's moving at angles. And that means that we do have to take it to another step, basically, when we're doing our solutions. The questions can be intimidating. What I'm going to be showing you here isn't like, this is what it is by definition. No, I'm just going to show you an example. This is an example. It is not every example by any stretch of the imagination. It's just a basic standard sort of 2D question. So you can see how we're using the ideas that we previously have from vector problems and 2D vectors and how we use that now with the idea of conservation of momentum. So as you work through this, as you look through this with me, one thing that I would suggest is it's probably going to be beneficial for you to look back at it again later on. Sometimes it can be a little bit overwhelming once you start seeing all the numbers. Then that's the other thing you should also be trying is at some point actually crack out your calculator and make sure that you're actually entering in things correctly so that you get the same numbers that I'm showing here. You can pause the video a few times and just double check that you're doing all the trig sort of things correctly. So the example that we've got is a 1.20 kilogram red ball moving to the right at 17.1 meters per second, strikes a stationary 2.31 kilogram blue ball. If the final velocity of the red ball is 13.5 meters per second at 23.0 degrees above the horizontal, determine the final velocity of the blue ball. Now, this can in itself seem sort of intimidating because there's a lot of stuff being talked about here, but I wouldn't be overly scared by it or something like that. You just have to break down the pieces. A few things, like when it talks about the red ball moving to the right, remember, in physics, we never want to talk vague about anything. If we say the red ball is moving to the right, we mean it is moving precisely to the right. So in our diagram, we will show a red ball initially moving exactly, completely to the right. It hits a stationary blue ball. That one is just sitting there. It doesn't have any momentum because it's not moving. And that's going to be something that makes this question a little bit easier. The blue ball has no momentum in the beginning. But after that collision, the red ball is moving at an angle. And I'm saying it's moving above the horizontal, 23.0 degrees. Now what I mean is, originally the red ball was coming in horizontally. Now it's going up at an angle, above the horizontal, above the original trajectory that the ball had, if you want to think of it that way. That means that when the red ball struck the blue ball, it couldn't have hit it dead on, because then it would have been a 1D collision. So sometimes you'll see this referred to as a glancing collision or something like that. It means that the red ball coming in and the blue ball, they had to be just a little bit off so that the red ball would hit and then go shooting off like that. That also implies that most likely the blue ball went down below the horizontal after the collision. Kind of like if you imagine a couple of pool balls hitting each other on a pool table. So what I would probably start with is just a quick little diagram for myself. And I like to write them out this way. I like to show what was going on, in this case before, because I've got all that information, the vector that represents the red ball, showing its mass and the velocity it's traveling at. For now, that's all I've got. I show it kind of coming in, so it's going to do that glancing collision with the blue ball. The collision occurs, and afterwards, the red ball is going up at a 23-degree angle above the horizontal. I'm giving its mass and velocity again. I don't know anything for sure about the blue ball. I don't know its angle. I don't know its velocity. I know its mass. That's one thing I do know. But that's all the stuff that I'm going to be looking for. I'm trying to find out information about the blue ball after the collision. Now, what I know for sure is that the total momentum over here before they collided and the total momentum after they collided, those are the parts that must be equal. Total momentums. And that's the other thing to remember. I sometimes see people do some really funny stuff with these questions because it is called conservation of momentum, not conservation of velocity. We can't do this based on velocities. Please don't do that. Don't set up your whole question just based on the velocities, because then you're not taking into account that this is conservation of momentum. So, at the start of this question, what I usually want to do is I want to try to get the numbers I can, look at what part of the question do I have all the information about. In this question, I have all the information about what's happening before, and then later on in the question, as I'm figuring things out, that's when I'll start attacking things that are happening after, because that's where I'm missing some information, where I don't know everything. So, looking at the before the collision part, I know that the red ball has 1.20 kilograms mass, moving at 17.1 meters per second. So I just calculate the momentum. I have to do this. Don't skip this. Don't say, oh, I don't. Shortcuts are not working for you in these sorts of questions. You've got to do all the work. So mass times velocity gets me the momentum. I'm also skipping sig digs right here. You're going to see I do that a lot over the next few minutes, only because I'm only going to round off at the very, very end for my final answers. So I know that about the red ball. What I can do is break it into its two components. Now you might look at this and say, well, where's all the math and stuff to do it? I don't need to do any math for this, because I know that the red ball is entirely moving to the right. That's the only thing it's doing. So all of its momentum is all x component. None of it is y component. There is no y component. But again, don't just skip that. Record these things, because you're going to see, especially when the questions are more complicated, always breaking up the problems this way will make your life easier, I promise. You come up with a system and you follow it. The blue ball. Well, this one's kind of easy. The blue ball, P equals mv. I've got its mass, I've got its velocity, 0. 0 times, I don't care what it is, the momentum is 0. Now again, this is going to be the part that's kind of like, duh, of course. X component, 0. Y component, 0. Of course, if it has no momentum, the X and Y components of 0 are both 0. But the blue ball could have been moving. And so always, again, do the questions the same way, have that system that works, and then you can use it for any problem. Now, what I'm looking at now is that essentially what I've done is I have taken a two-dimensional problem, because that's what this really is overall. Taken a two-dimensional problem and I've broken it into x and y components. The x components, all on their own, are like their own little mini 1D. And the y components, their own little mini 1D. This is 1D, this is 1D, together they're 2D. But I can do the 1D stuff easy. I can say things like, take these two numbers, add them together, and get the total x component of the momentum, 20.52. I don't think you need to take out your calculators for that one, I hope. For the y's, same deal, 0 plus 0 equals 0. But again, I can't stress enough, these numbers are not always going to look this easy. You're going to sometimes have to do trig and stuff to get these. We'll see this in a moment as we do the after collision stuff. But the reason why I'm doing all of this was to get these two values. And they're the ones that I must have, because before the collision, I know that the total x component of the momentum is 20.52 and the y total is 0. The great part is these numbers have to be the same after the collision as well. They must be, otherwise momentum wouldn't be conserved. So I take this and I flip it to after the collision. But notice, those parts stayed the same. They come with me. So, let's look at the red and the blue ball again, but this time after the collision. For the red ball, I know its mass and its new velocity after the collision gives me a brand new momentum, and with a kicker, it's at an angle. So now, I have to break that up into components. I have to draw a regular little triangle that shows if I have the red ball moving with a momentum like this, it'll have two components, one pointing to the right and the other one pointing up. So I need to find those two components. To find the x component, and draw out the little diagram for this and double check yourself on it, cos is going to be the best way of going after it, because the x component is the adjacent side, and this is the hypotenuse. So I'm going to have to take it, I have to manipulate my formula to solve for the adjacent side, which is the x component, the cosine of 23 degrees times the hypotenuse gives me, again, an unrounded number, 14.912. Do the same sort of thing for the y component. For the y component, I chose to do sine. You could have done tan. You could do Pythagoras. It doesn't matter, because once you have this and the hypotenuse, you can use other trig. But the reason I don't want to use those myself is, if I did this calculation wrong, and then I used it with tan or Pythagoras, this one has to be wrong also. If I do this kind of with the freshest numbers that I still have, a number that's only been through my calculator once, the hypotenuse, and going after the opposite side, which is the y component, I have the best chance of maybe at least getting this one still right. So I went through all the stuff. I solved for the opposite side, which is the y component, put in my angle again, put in the hypotenuse, and I got 6.3298. So that means I have an x component that's pointing to the right, and I've got a y component that's pointing up for that red ball. Now here's the nifty part. Remember that whatever's happening with the blue ball, that's what we're looking for. The x plus whatever is happening with the blue ball has to equal this still. The y plus whatever's happening with the red, whatever's happening with the blue, have to add together to 0. That just has to be. Otherwise, I wouldn't have conservation of momentum. That means that finding out at least the y component of the blue ball is like the easiest one ever for this. Because since they have to add up to 0, if this one is up positive 6.3298, this one must be negative 6.3298. Now I wrote it out kind of a long way here. I said my y total, which is this, has to be equal to what the red ball is plus the blue ball. And then I solve for blue ball, because that's going to be the total minus the red. 0 minus the number that I got right there equals a negative value. This is just me showing sort of the long way of reasoning it out. And that can be helpful to you when the numbers aren't just 0, for example. But really, for this case, it is pretty fast. This y has to be exactly canceled out by the blue ball's y component, because that way they have 0 y momentum. And that comes from way back at the beginning when there was no y component. Okay? The x is going to look a little bit longer. Again, I wrote out that the total, this number, has to be equal to red plus blue. I solve for the blue. That means it's the total minus the red. So I take the total minus the red ball, and I find out that the blue ball must have 5.608. Now be careful here, because sometimes you might get a negative number or whatever. You've really got to pay attention to the signs on these, because they do tell you direction. This tells me the y component is down. This tells me the x component is to the right. So the blue ball is moving to the right and down. These are my momentum components of the blue ball after the collision. I can use those to build a triangle, like this. The blue ball x and y components can give me its resultant, what it's actually doing, and I can also get the angle from that. So I go ahead, I set up some Pythagoras, I've got my two sides, and I want the hypotenuse. So I go ahead and I drill those numbers in. Don't forget stuff like squaring each of these and then square rooting the whole thing. Those are easy things to miss. Gets me my answer, 8.457 kilogram meters per second. That's a momentum though. That is not my velocity. And way back, I know it seems like a long time ago now, I was asking what is the velocity of the blue ball. So I do need to take that and use the good old-fashioned formula for momentum to say, I have the momentum, divide it by the mass, that'll give you the velocity. So the ball is moving, the blue ball is moving at 3.66 meters per second. And now I'm rounding for sigdigs because I'm at the end, almost. And I go back and I look at all my original numbers, 3 sigdigs all the way. So from the numbers I had at the beginning. So 3 sigdig answer there. But am I done yet? No, because the question said, what's the velocity? That's why I must calculate the angle. This is not maybe should I, or no, it's a requirement. If the question says velocity, you are required to give a direction. If the question only said speed, then this is the finished product, done. But the question said, what is the velocity? So I must do it. Oh, also sometimes we might even just say, what is the magnitude of the velocity? That again just really means speed. It means forget the angles and stuff. But I am going to get that angle. I would suggest using these 2 sides to do a quick little bit of trig. Use tan. I usually want to find the angle at the tail of my resultant as being the angle that I'm measuring. So I've got my opposite and adjacent sides, put in the numbers, get an angle. Please make sure that when you're doing this like short answer, formula, substitution, answer, the whole works. And yes, angles have sigdigs. And so since all these numbers, everything that I was doing here to do all of this stuff was originally based on numbers that had 3 sigdigs, this is 3 sigdigs also. Okay, we gotta make sure that we've got that. Probably at this point, I would usually make some sort of final statement where I would say 3.66 meters per second at an angle of 48.5 degrees below the horizontal, below the original path of the red ball, because that's really what this is. It's going below that original path. Something like that. I might avoid saying things like saying east 48.5 degrees south, only because maybe those aren't the directions I have. It wouldn't be too bad if I used that here though. That would be acceptable still. I just might not do it though because in the original question they didn't state directions like that. So what I'd suggest is you go back, you double check yourself on all the number crunchies on this thing, make sure that you can follow along with sort of the process, and then try other examples where, for example, the blue ball is moving originally, or the red and the blue balls originally, before the collision, have angles also, so you have to do their components. You just do the same process for all the questions, where you're always saying, I need to break down vectors that are traveling at weird angles and stuff. I need to break those into their components, being careful to assign directions, like up is positive, down is negative, to the left is negative, to the right is positive. Make sure that you're putting those signs on your values when you get your components, if they don't pop out automatically that way, and use that to solve your way through these 2D problems. So good luck with that.